looking at transformation to the stationary reference frame. We started off with the machine description in the 3-phase, and then from that we went on to the alpha beta 0 reference frame, both alpha beta 0 for the stator and alpha beta 0 for the rotor, and we said that the 0 sequence is most likely not there, so we can neglect the 0 sequence component. And this alpha beta reference frame then has two axes. One is the alpha s axis, that of the stator, and then you have the beta s axis, that of the stator. The alpha s axis has an MMF oriented along its direction due to an alpha s coil, and then similarly the beta s axis has another MMF oriented along that, and we also then have an alpha r axis and then a beta r axis which is at 90 degrees to that. So you have a beta r coil and an alpha r coil. So this is a representation of your 2-phase machine, neglecting 0 sequence components. And for this we can write the expression in terms of voltage equals R into I plus P of inductance matrix into the I vector. V is in the alpha beta reference frame for the stator and alpha beta for the rotor. I is also alpha beta and alpha beta, so alpha beta here and alpha beta there. The inductance matrix we have seen can be written by observation, and the inductance matrix can then be written as L, let us call it alpha beta, so that there is no confusion. The inductance matrix can then be written as Ls of the stator. To distinguish this from the self inductance in the 3-phase case, let us call this as Ls bar, and then there is a question of mutual inductance between the alpha s and beta s axis, and we observed yesterday that that is 0. So the mutual inductance is 0. Let us give some more space here. So mutual inductance is 0, and then you have MSR into cos of theta r, representing the mutual inductance between the alpha s and the alpha r axis, and then you have minus MSR sin theta r, represents the mutual inductance between the coil on the alpha s axis and the coil on the beta r axis. And the second row would then represent the flux linkages or the inductance of the beta s axis, and since the two coils are identical on the alpha s and beta s axis, the self inductance term is the same. And then you have between beta s and the alpha r axis, so that is sine of theta r into MSR bar, and then you have MSR bar cos theta r, and then here you have MSR bar cos theta r, and then this is minus MSR bar sin theta r, and then here you have MSR bar sin theta r, and then cos theta r. Here you have the rotor inductance there is no mutual inductance between the alpha r and beta r axis, because again they are at 90 degrees, and therefore there is 0 here and then Lr here. So this is the inductance matrix neglecting 0 sequence components. If 0 sequence component was there, you want to include that, then you would have one column here extra, one column here extra, one row here extra, and one row here extra. Only the term coming here will have an entry, and that corresponds to the leakage inductance of the stator, and similarly here there would be another entry which corresponds to the leakage inductance of the rotor. We already know that from the earlier derivations that we have done, going from 3 phase to 2 phase. Now we can see that this inductance matrix can be conveniently divided into 4 sub matrices. So this matrix we can call as L11, this sub matrix L22, this is then L12 and L21. Obviously we can see that L21 is equal to L12 transpose. So this expression V alpha beta equals Ri plus P into Li describes the electrical system of this 2 phase machine, and we see that the inductance matrix depends on the rotor angle, which is what we observed in the last lecture. And in order to get rid of that, we said that one can transform the rotor to a stationary axis, having observed that the rotor angle arises or occurs in this description because the rotor is moving with respect to stator, and looking at the MMF produced by the rotor alpha r axis and the beta r axis at a given angle phi, yesterday we found that the same MMF could have been developed by 2 coils that are placed here, one on the alpha s axis along the same axis as alpha s, another along the beta s axis. So if we consider 2 fictitious coils, one along alpha s axis and another along the beta s axis, both representing together the MMF that would have been produced by the alpha r and beta r excitations, then these 2 MMFs being equal, one can define a relationship between the flow of currents here. We will call this current as I. This is the flow of current, even though this coil is along the alpha s axis, this flow of current is determined by both I alpha r and I beta r, and therefore we will call this as current flowing along the alpha axis due to the rotor currents, both the rotor currents. So we call that as I r with the subscript alpha. Similarly here the current that is flowing is I r with a subscript beta. So we defined a relationship yesterday between the 2 currents I r alpha and then I r beta. This relationship we found that it was cos theta r minus sin theta r, sin theta r and cos theta r multiplying I alpha and I beta. So these are the currents that are flowing actually in the rotor, of course in the 2 phase axis of the rotor, not the 3 phase machine, and these can then be equivalently thought of as being some currents, the same MMF being produced due to these 2 currents which are flowing now. These currents are flowing in the pseudo-stationary fictitious alpha s winding and the beta s winding. So having defined this, we can now observe that if you know these 2 currents, you can get these two currents, and similarly if you know these two currents it is feasible to get those two currents. How can you do that? You need to invert this and bring it over here, and you see that the determinant of this is simply cos square theta r plus sin square theta r, which is 1, and therefore the inverse of this is simply the transpose of this, and therefore if you call this by the matrix C22, then we can say that I alpha beta is equal to C22 transpose into I r alpha beta. So this enables you to go from alpha beta to fictitious coil or fictitious coil to alpha beta, and as we observed yesterday, this does not have zero sequence. If we have zero sequence, that does not go through this equation, zero sequence is retained as it is. So you need to add one row of zeros and two zeros here, with the diagonal entry being 1, and the same zero sequence therefore comes here. Now this defines a relationship between I variable here and I variable here. We would like in this case, in order to transform the variables from the rotating reference frame to the stationary reference frame, then we would like to have power invariancy, which then means that V alpha beta I alpha beta transpose into V alpha beta, you would like it to be I r alpha beta transpose into V r alpha beta. This is the power in fictitious coils. This is the power in alpha beta coils in the rotor, and therefore if we are to get this, we can now use this relationship and then say that replace this expression, that is C22 transpose into I r alpha beta, this whole thing transpose multiplied by V alpha beta equals I r transpose alpha beta into V r alpha beta, which then means that I r transpose alpha beta into C22 transpose is C22 into V alpha beta equals I r transpose alpha beta into V r alpha beta. So looking at this expression, we then conclude that V r alpha beta equals C22 into V alpha beta. Therefore the transformation for voltages is the same as the transformation for this. I alpha beta here and I r alpha beta here are related by this C22. Similarly here also it is related, and therefore we have defined that relationship between this voltage and the fictitious coil voltage. Now having defined all this, we now need to see how we can apply this to this expression for the two phase machine. Now we want to transform only the rotor to fictitious coils. Here the stator is already stationary, and therefore if you transform the rotor to stationary here, then all these four are stationary with respect to each other. We hope therefore that the rotor angle will not appear in the equations. That is what we need to verify now, and therefore we will define an augmented matrix C, which is 1 0, or let me put it in a short form. This is the identity matrix U, which is 2 by 2, and then 0 matrix and C22. So, having defined this, then we can now define these two, that is I R alpha beta equals alpha beta of the rotor and alpha beta of the stator. This is therefore equal to C times I alpha beta and alpha beta. Similarly, you would have the relationship V R alpha beta of the stator, alpha beta of the rotor is equal to C times V alpha beta and alpha beta. Or if you want to put it in an expanded form, what this matrix simply means is that V alpha, V beta, V R alpha, V R beta is 1 0 0 0 0 1 0 0 0 0 cos theta minus sin theta r 0 0 sin theta r cos theta r multiplied by V alpha, V beta, V alpha, V beta. So, that is what this relationship means, and therefore, we see that we are going to retain the stator voltages as it is. There is no change in the stator variables. The rotor variables, however, undergo a change from the alpha beta axis of the rotor to alpha beta fixed on the stator. So, these two variables are pseudo stationary variables in the stator reference frame, these two variables are in the rotor reference frame. Similarly, one can define this, these two equations are similar. Now, using this, we would like to see what would happen to the machine description if we use these two equations and substitute it back in our machine description that we wrote. So, our machine description was V alpha beta equals R I alpha beta plus derivative of the flux linkages Now, substitute these equations. V alpha beta is nothing but C inverse into V R alpha beta, and therefore, we can substitute it there. This V R alpha beta is this matrix where alpha beta is stator variable and the rotor is also referred to alpha beta. So, we have C inverse V R alpha beta equals R into C inverse I R alpha beta plus derivative of L alpha beta multiplied by C inverse I R alpha beta. So, having substituted these expressions in the original machine equation, voltage equations, this is what you get, and in order to get V R alpha beta you need to multiply by C matrix throughout, and therefore, you can multiply this by C and multiply this by C as well. And here you have C inverse appearing. If you look at the matrix we have here, C inverse is going to be C transpose, as you can see from this, and therefore that should be easy to observe. Otherwise I would leave you to verify that C inverse of this is indeed C transpose, and therefore this can be written as C R C transpose I R alpha beta plus C times P of L alpha beta C transpose I R alpha beta. Now this is what we need to expand, and we will try to do that now. This matrix C R C transpose is fairly easy to simplify. I will leave that again to you as an exercise. It is easy to show that this matrix is nothing but R, and therefore this part of the expression is fairly easy. We need to focus on this part of the expression, and therefore that can now be written as I times R alpha beta plus this expression can be written as C L alpha beta C transpose P of I R alpha beta plus C times P of L C transpose into I R alpha beta. So we need to evaluate this matrix CLC transpose and CPLC transpose, which we will try to do now. Let us try to simplify the expressions. We will consider the term L alpha beta into C transpose. So this can be written as L11 L12 L21 L22. L21 is nothing but L12 transpose, so we will make use of that here, into C transpose is nothing but identity matrix 0 0 C22 transpose. So this is L alpha beta C transpose. So this can be written as L11 L12 C22 transpose L12 transpose and L22 C22 transpose. So what we need to evaluate are L12 C22 transpose and L22 C22 transpose. So L12 C22 transpose is nothing but, you can see that L12 has MSR dash that is common, so we would take that out, and the remaining terms are cos theta r minus sin theta r sin theta r and cos theta r multiplied by C22 transpose, and we do not have the C matrix here. So let me write the C22 matrix here. C22 was cos theta r minus sin theta r sin theta r and cos theta r, and therefore the C22 matrix is cos theta r sin theta r minus sin theta r and cos theta r. This whole thing multiplied by MSR bar is this term L12 into C22 transpose. So this is therefore equal to MSR bar the first term is cos square theta plus sin square theta, that is 1, and the next term here is cos theta sin theta minus sin theta cos theta, so that is 0, and here you have sin theta cos theta minus sin theta cos theta is 0, and sin square theta plus cos square theta is 1. So L12 C22 transpose reduces to a fairly simple matrix, that is what you have. The next term that you need to get is L22 C22 transpose. L22 is not depending on the rotor angle, it is simply LR LR 0 0, and therefore this can be written as LR multiplied by the identity matrix 2 by 2 into C22 transpose, which is simply LR dash into C22 transpose. So it is the same C22 matrix that you have multiplied by LR. Having defined these two, then if you look at the expressions that you have, there are two things that we need to do. One, we have determined L alpha beta C transpose, and we now need to, on the one hand, pre-multiply by C, on the other hand you need to differentiate this and then pre-multiply by C. So let us first pre-multiply by C and then we will do the differentiation. So if you now pre-multiply this by C, what we are trying to do now is C L alpha beta C transpose. So this is identity matrix 0 0 C22 multiplied by this term is what we have determined earlier, so that is L11. L12 C22 transpose is what you have as MSR bar into identity matrix U, and then you have L12 transpose. L22 C22 transpose is nothing but LR bar into C22 transpose. So that is what you have, and if you multiply this, what you get is L11, the first term reduces to L11, the second term reduces to MSR multiplied by identity matrix, the third term reduces to C22 into L12 transpose, and the fourth term here reduces to C22 LR C22 transpose. Remember, LR is a scalar, it is not a vector, and therefore this reduces to the scalar LR dash into C22 C22 transpose, and we know that C22 transpose is nothing but the inverse of C22, and therefore this term reduces to LR into identity matrix. Here you have C22 into L12 transpose, we have already determined L12 into C22 transpose. So this term is nothing but the transpose of this, and this is already MSR into U, and therefore this is nothing but MSR into U. So we have determined what is CL alpha beta into C transpose, that is nothing but this matrix. So we will now keep this aside for the moment and focus on the derivative of LC transpose. So we will write this somewhere on the board, we will write it here. So C L alpha beta C transpose is nothing but L11 and then MSR bar into identity matrix, MSR bar into identity matrix, and this matrix is the same as L22, so we will retain it as L22 and we can remove this expression. Now we need to find out the derivative of LC transpose. So let us try to do that. The derivative of LC transpose. So yes, L alpha beta into C transpose is L11 L12 transpose. L12 into C22 transpose was this, so that is MSR into U, and this one is LR bar into C22 transpose. Now if you take the derivative of this expression, each of these terms has to be differentiated. Derivative is with respect to time, and you see that L11, the inductance matrix here, that is the first sub matrix here, this contains only fixed elements, there is not anything that is varying with respect to time, and therefore the derivative of L11 is 0. So the derivative of this is equal to 0 in the first place. This does not vary with respect to time. MSR into U, MSR bar into U, you can see this matrix, there is nothing again varying with respect to time, therefore that is also 0. L12 transpose, L12 is a matrix that is varying with respect to time because there is rotor angle, and rotor angle is going to change continuously as the rotor rotates. This will vary with respect to time. So this is P L12 transpose, and here you have C22. C22 again has the rotor angle here, therefore C22 also varies with respect to time. So therefore this is P LR bar into C22 transpose. And now let us evaluate those expressions. Maybe we will do that here. We do not need these anymore, so we will do this here. P of L12 transpose is nothing but the derivative of this expression. So if you look at this, MSR bar is there everywhere, that can be taken out. So MSR bar, and then you have this term, derivative of cos theta is sin theta r, and then you have derivative of sin theta r, that is cos theta r, and then you have derivative of minus sin theta r, that is minus cos theta r, and then you have derivative of cos theta r, which is minus sin theta r. So you have minus sin theta r multiplied by d theta r by dt. So this is then the first term there, and the second term there involves derivative of C22 transpose. C22 is already there, and we need to look at C22 transpose. So P LR bar into C22 transpose is then LR bar multiplied by cos theta r, derivative is minus sin theta r, and then cos theta r here, minus cos theta r and minus sin theta r multiplied by d theta r by dt. We need C22 transpose, so I have taken the transpose, cos theta r becomes minus sin theta r, this sin theta r would go there, and the derivative is cos theta r and the other two terms. So this is what you have, and what we need to do now is to evaluate the last term. We need to find out we need to find out C of P L alpha beta into C transpose, and therefore let us do that. C is identity matrix 0 0 C22 multiplied by the derivative of this, as we have already written down, the first two terms are 0, and then you have P L12 transpose, and then you have P LR bar C22 transpose. This is what you have, and this term then simplifies to 0 multiplied by 0 is 0, and then 0 multiplied by 0 again is 0. The third term is 0 plus C22 into PL12 transpose, and the last term is C22 PLR C22 transpose. So, we now need to evaluate this term and this term. So, let us do that. We do not need this expression anymore. So, let us get rid of that. So, essentially then we need to multiply this matrix and this matrix by C22, that is what this expression says. So, let us do that. C22 is cos theta r minus sin theta r, sin theta r and cos theta r, that is C22, multiplied by P L12 transpose. P L12 transpose we already have here, and therefore that is MSR bar multiplied by minus sin theta r cos theta r minus cos theta r minus sin theta r multiplied by d theta r by dt. So, that is going to give us MSR bar into, the first term is cos theta minus sin theta and plus sin theta cos theta, therefore this term is 0. The second term gives you cos square theta plus sin square theta, and that is 1. This term gives us minus sin square theta minus cos square theta, therefore this is minus 1, and the last term gives us sin theta cos theta minus sin theta cos theta, therefore this is 0. So, we have found out this term. This is nothing but C22 PL12 transpose, that we have found out. The next term is C22 P LR C22 transpose. We have to make use of this. So, C22 P LR bar C22 transpose is nothing but cos theta r minus sin theta r and sin theta r and cos theta r multiplied by LR bar, you keep that separately, and multiplied by this term which is here. So, minus sin theta r cos theta r minus cos theta r minus sin theta r multiplied by again d theta r by dt. So, that gives us LR bar multiplied by, the first term is cos theta minus sin theta plus sin theta cos theta, therefore this is 0, and then you have cos square theta plus sin square theta, that is 1, minus sin square theta minus cos square theta becomes minus 1, and then you have sin theta cos theta plus cos sin theta cos theta minus sin theta cos theta, therefore this is 0. So, we have now evaluated all the sub matrices and we need to put them together to see what it looks like. So, let us do that assembly here. you have C P L alpha beta into C transpose is what you are going to have, and this is, if you see, the first two entries are 0 matrices. So, you have 0 here and 0 here. The next two entries are available in these two places. The first entry is MSR bar, I missed this d theta r by dt, is MSR bar into a description like this 0 1 minus 1 0. So, let me write this slightly bigger to accommodate that. So, this is MSR bar into 0 1 minus 1 0, and then here you have LR bar again into 0 1 minus 1 0. So, we have evaluated all the sub matrices that are of interest. So, let us now put all these equations together and see what it looks like, which we can do it again here. So, what we now have is V R alpha beta of the stator and alpha beta in the rotor referred to the stator side is nothing but R into I R alpha beta plus C L alpha beta C transpose into Pi is a matrix which is nothing but L11 and then MSR bar into U, and this is again MSR bar into U, and then L22 P I R alpha beta plus this matrix which is 0 0 MSR bar into 0 1 minus 1 0 LR bar into similar 0 1 minus 1 0, this multiplied by d theta r by dt multiplied by IR alpha beta. So, now you see that this matrix does not have the rotor angle in it, this matrix also does not have the rotor angle in it, the resistance anyway does not have the rotor angle in it. Therefore, the electrical description of this system now does not have the rotor angle involved, unlike this inductance matrix where you had the rotor angle inside this. So, we can now try to compress all these equations and try to write this as the in a form which is similar to what we did earlier, the so called operational impedance form, operational impedance matrix, where we will expand this term V alpha, V beta. Remember, the stator variables have been retained as it is, no transformation to the stator variables, and then you have Vr, the rotor variables have been transformed on the one hand to the alpha axis of the stator and on the other hand to the beta axis of the stator. We are going to write this as V equals some Z multiplied by I. So, we need to pick terms from this description and then put it here. So, the first term here will come from the first term of this R matrix, first term here and the first term there. So, the first term here is the resistance of the stator that will come, and then you have the self inductance of the stator. L11 matrix, remember, has an Ls bar and Ls bar. So, you have plus Ls bar into P, it is going to multiply the vector I. Then the second term here will not have any entry, the resistance has entries only along the diagonal, off diagonal entries are 0. So, there is nothing due to the resistance. Here also there is nothing here, the 1 2 element is 0. So, the second term would again be 0, and then there is nothing coming from here as well, therefore, this term is 0. The third term here, nothing would come from the resistance matrix, whereas here it is MSR bar into identity matrix, and therefore, this is MSR bar multiplied by P, and then the last term is again 0 there. So, going in this manner, if you select the appropriate terms from all the matrices and combine them, what you would find is here again it is 0. So, this entry is Rs plus Ls bar into P, and then 0 here again, and then MSR bar into P, and here you have MSR bar into P, and then MSR bar into omega r. This term comes from the matrix here, MSR bar d theta r by dt I am writing as omega r, and here it is Rr plus Lr bar into P, and here you have Lr bar multiplied by omega r, and here you have minus MSR bar into omega r coming from this term, and then you have MSR bar multiplied by P coming from this term, and then you have minus Lr bar multiplied by omega r coming from here, and then the last term here is Rr plus Lr bar multiplied by P. So, this is then the operational impedance form of the electrical equations. The zero sequence component, as we have been mentioning earlier, has been left out. If the zero sequence component is going to come in, that we have left it untransformed, and therefore, you will have another row here and another row here, one column in the middle here, one column in the middle there. There would be only the diagonal entries here and here, which will correspond to Rs plus the leakage inductance times P, and similarly there Rr plus the leakage inductance of the rotor times P. Now, this matrix is then the operational impedance matrix in the stator reference frame. Why stator reference frame? Because the stator coils are already there in the stator, of course. The rotor coils have now been referred to the stator by having fictitious coils alpha and beta. So, all the coils are now in the stator, and this description will then give you the behavior of the machine as seen from the stator. This description is more easier to handle because the impedances here are not dependent on the rotor angle, and therefore, if you can write this expression again as the same equation as R into I plus an inductance matrix L alpha beta Pi plus another matrix which you call as G omega R into I. G matrix, L matrix and R matrix are not functions of the rotor angle, and therefore, it is easy to solve them on a digital computer, these matrices being fixed. So, that is one of the advantages of having the description in this form. Now, it so turns out that by remembering a few rules, this matrix can also be written by observation, and by understanding those rules, this matrix can also be extended to different situations. We shall see how to do that in the next lecture and more utilities of the system description of this kind. We will stop here for today.